All right, let's look at section 1.4, composition of functions. So let's hop right into it. When the output of one function is used as the input of another, we call the operation a composition of functions. We write f of g of x. We read this f of g of x, or we can read this as f composed with g at x. An alternate notation for composition includes this composition operator that we'll see. It's like an open circle like this, or it's a blank circle. There's nothing inside of it. So you would see something like f of g of x. This is the same thing as this f of g of x. These are equivalent. So let's hop into an example. Let's see. Let's say, suppose C of S gives the number of calories burned when doing sit-ups. And S of T gives the number of sit-ups a person can do in T minutes. Let's interpret what C of S of 3 might mean. So notice that inside this composition is S of 3. Since the input in this function S is time, the 3 represents 3 minutes. So in this case, S of 3 is the number of sit-ups a person can do in 3 minutes. If I then take this output and use it as the input for this C of S function, C of S of 3 will give us, because remember C of S is the number of calories burned when doing sit-ups, C of S of 3 will give us the number of calories that can be burned by doing the number of sit-ups that can be done in 3 minutes. So this is just this is just like a theoretical example, or like an example of where we might use function composition. Let's look at how to do function composition using tables and graphs. So whenever we compose functions, we start by working with the inside. We evaluate the inside, and then we take that and we provide it as the input to the outside function. So let's jump right into, I'm going to give us two tables, and using these tables, we're going to evaluate f of g of 3 and g of f of 4. So these tables would be, let's see, x and f of x here. I have 1, 6, 2, 8, 3, 3, 4, 1. And I have this other table here, x and g of x. That is 1, 3, 2, 5, 3, 2, and 4, 7. So if I want to find f of g of 3, I need to look at the table that has the g of x in it. I need to find what g of 3 is. So I look at this right-hand table. I look at my x value of 3. I see that g of 3 is 2. I'll write this over here on the right. G of 3 is 2. Now I'm looking for f of g of 3. And keeping in mind that g of 3 is 2, this is the same thing as looking for f of 2. And f of 2, I look at this left-hand table, and I get f of 2 is equal to 8. Let me see if I can scroll to the right a little bit less than that. There we go. So f of g of 3 is f of 2, which is 8. Same idea if I'm looking for g of f of 4. I'll write this underneath. So g of f of 4. The first thing I do is I look for what f of 4 is. So I'm looking in this left-hand table. F of 4 is 1. So because f of 4 is 1, this means that g of f of 4 is g of 1. And g of 1 is 3. Let's do a few more real quick. We can do let's see, f of g of 1. So f of g of 1, well, g of 1 is 3, so this is f of 3. F of 3 is 3. G of f of 3, this is g of f of 3 is 3, and g of 3 is 2. Let me see which one next. Let's look at using formulas. So let's have this one. Given that f of t is t squared minus t, and h of x is 3x plus 2, let's evaluate f of h of 1. So notice that the inside evaluation here is h of 1. So let's start out by finding what h of 1 is. H of 1 is, well, h of x is 3x plus 2, so h of 1 is 3 times 1 plus 2, which is 5. This means that f of h of 1 is, well, h of 1 is 5, so this is f of 5, which is 5 squared minus 5, which is 25 minus 5, which is 20. Let's do the same for h of f of negative 2. So I'm going to find what f of negative 2 is first. This is negative 2 squared minus negative 2. Negative 2 squared is 4. 4 minus negative 2. This is the same thing as 4 plus 2, which is 6. Which means that h of f of negative 2 is the same thing as h of 6, which is 3 times 6 plus 2, which is 18 plus 2, which is 20. This is just a coincidence that this is the same answer as our last one. This is just a coincidence. Let's see here. Let's use the same function. Let's use the same f of t. F of t is t squared minus t. All right. And let's find what f of x plus 2 is. All right. So f of x plus 2, this is going to be where I replace all of my t's with x plus 2. So this is going to be x plus 2 quantity squared minus x plus 2. I can distribute this out. Remember that if I square something, I'm just multiplying it by itself. This is what I have. Now I can use my distributive property, and I can write this as x times x plus 2 plus 2 times x plus 2 minus x plus 2. And now let's go ahead and distribute everything. This is x squared plus 2x plus 2x plus 4 minus x minus 2. When I combine all of my like terms, I have 4x minus x, that's 3x. I have 4 minus 2, that's 2. So I have x squared plus 3x plus 2. Let's also find, let's see. Let's take g of x equals 3x minus square root of x. Let's evaluate g of t minus 2. Same idea here. Everywhere I see an x, I'm going to replace it with t minus 2. So g of t minus 2 is 3 times t minus 2 minus the square root of t minus 2. This is 3t minus 6 minus the square root of t minus 2. That's as simple as this one gets. Let's try something maybe slightly more complicated. Let's try let f of x equal x squared and g of x equal 1 over x minus 2x. Let's find f of g of x and g of f of x. So if I want to find f of g of x, this is saying everywhere I see an x in f of x, replace it with g of x. Or this is the same thing as finding f of g of x is 1 over x minus 2x. So anywhere I see an x in f of x, I replace it with this inside statement, with this argument. This is going to be 1 over x minus 2x squared. I suppose we can leave it like this. Finding g of f of x is it's exactly the same process. I can just say that this is the same thing as finding g of, well, f of x is x squared. So g of x squared, that's 1 over x squared minus 2 times x squared, or just 1 over x squared. Oh, not plus, sorry. Minus 2x squared. We can look at an example, then we'll talk about domain, and then we'll be done. A city manager determines that the tax revenue are capital R here, in millions of dollars, collected on a population P, 1,000 people, is given by the formula R of P equals 0.03 P plus the square root of P, and that the city's population in thousands is predicted to follow the formula P of t equals 60 plus 2t plus 0.3 t squared, where t is measured in years after 2010. Find a formula for tax revenue as a function of year. Well, since we want tax revenue to be a function of our year, we want our year to be the initial input, and for revenue to be our final output. To find the revenue, we first need to know our city population and then use that result as an input into the tax function. This means that we need to find R of P of T. If we find R of P of T, this is the same thing as finding R of 60 plus 2t plus 0.3t squared. And this will be, I'll write this on a new line. This is going to be 0.03 times 60 plus 2t plus 0.03 t squared plus square root of 60 plus 2t plus 0.3 t squared. So this composition gives us a single formula that can be used to predict the tax revenue during a given year without needing to find the intermediary population value. For instance, if I want to find the tax revenue in 2017, this is when t equals 7 because t is measured in years after 2010. Then I'd find R of P of 7, which is going to be 0.03 times 60 plus 2 times 7 plus 0.03 times 7 squared plus the square root of 60 plus 2 times 7 plus 0.03 times 7 squared. And if we type this into a calculator, we should get about $12.079 million, because our revenue formula gives us a number in terms of millions of dollars. And let's look at domain of compositions. So whenever we're looking at domains of compositions of functions, we have to take into account both the inner and the outer function. So let's look at this one. Let f of x equal 1 over x squared minus 1 and g of x equal the square root of x minus 2. So I have to take into account both the composition and the domain of the inner function, because if the inner function is undefined at a certain value of x, then I can't compose my function at that value, right? Let's find the domain. Of f of g of x. So let's notice here that the domain of g of x we're first going to look at the domain of our inner function. The domain of g of x, here I need for my x values to be greater than or equal to 2, right? I guess I can start from the beginning. I need for x minus 2 to be greater than or equal to 0, which means I need x to be greater than or equal to 2. Now, the composition here, f of g of x, this is 1 over the square root of x minus 2 squared minus 1. The square and the square root cancel here, so this becomes 1 over x minus 2 minus 1, which is 1 over x minus 3. So notice here that this composition is undefined when x equals 3. So x equals 3 also has to be excluded from my domain here, right? X can't be equal to 3. So I have to combine the two restrictions from the domain of g of x and the restriction that I found in my composition here, f of g of x. So I need all x values that are greater than or equal to 2, except for x equals 3. In inequalities, I would write this as 2 is less than or equal to x, which is less than 3, or x is greater than 3. In interval notation, I would write that this is 2 to 3, including this 2, but with this 3 I'll have a parenthesis, union 3 to positive infinity. And let me see what else we have here. I guess the last topic is just this small topic on decomposing functions. In some cases, it might be desirable for us to decompose a function, which means to write it as a composition of two simpler functions. So let's try to write f of x equals 3 plus the square root of 5 minus x squared as the composition of two functions. So we're looking for two functions that we can call g and h, so that f of x is equal to g of h of x. To do this, we need to look for a function inside of a formula for f of x. One possibility that we might notice here is that this 5 minus x squared is inside of this square root. Then we might say that, h of x will be my inner function. This will be 5 minus x squared. G of x would be 3 plus square root of x. And then we can check our composition to see if this works. I can try g of h of x. This is g of 5 minus x squared, which is 3 plus the square root of 5 minus x squared. So this works. This decomposition works. This isn't the only solution to this particular problem. You could have also said something like h of x equals x squared and g of x equals 3 plus the square root of 5 minus x. And this also we can compose in order to get this composite function, this more complicated function here. And this is it for 1.4.